I wanted to work through a problem that involves an electrical circuit in which there are resistors, and those resistors are arranged in such a way that there's both series resistors and there's parallel resistors. So a more complicated circuit than just pure series resistors or pure parallel resistors. So the circuit I'm thinking about in this problem is this one over here on the left. So this circuit contains a 6-volt battery. It's a source of 6 volts of potential difference, or 6 volts of electromotive force. We'll think of it as an ideal battery. No matter what current, it's going to supply 6 volts of electrical potential, or 6 volts of electromotive force. Connected across the terminals of the battery is an arrangement that consists of 4 resistors, and there are 3 distinct values for the resistors, R1, R2, R3, and there's also a multi-way switch. And using the multi-way switch, you can include or exclude parts of the circuit. So in the problem, we're told that if the switch is open, so the position that's drawn here, then 1 amp, 1.0 amps is drawn from the 6-volt battery. If the switch is placed into position A, then in that case, 1.2 amps is drawn from the circuit. And then finally, if the switch is placed into position B, 2.0 amps is drawn from the circuit. And so with that multi-way switch, we can reconfigure the circuit, including, excluding resistors in 3 different ways, with it either open or with it in positions A or B. We're told, as I say, that in the case of the switch being open, we draw 1 amp from the battery. In the case where the switch is in position A, we draw 1.2 amps from the battery. And in the case where the switch is in position B, we're going to draw 2.0 amps from the battery. And from that information, we've got to figure out the 3 different values of the 4 resistors in the circuit. So the first thing I did in solving this problem is to redraw the circuit, actually redraw 3 versions of the circuit corresponding to the 3 switch positions. So I redrew a version of the circuit where the switch was open. I redrew a version of the circuit where the switch was in position A. I redrew the circuit where the switch was in position B. These are the 3 drawings here on the left, here in the center, and here on the right. This is open, in position A, and in position B. And by redrawing these circuits, it will help me in writing down equations that describe the currents that are flowing in the circuit, the potential across the circuits, and the resistance of the circuit. So let's just go through them one by one. So let's think about the open circuit, the one on the left. In that case, all these arms, 3 arms in the center of the circuit diagram, they're all inactive. And current just flows around the outer loop in the circuit. So the current just flows through R1, then R2, and then R3. And there's no current, for example, through this 4th resistor. in the center of the circuit. And so I redrew that circuit, and it just involves 3 resistors in series with one another. So that's quite simple. Then I imagined when the switch was in position A. So when the switch is in position A, this upper inner arm of the circuit is then activated. It's then on, and current can flow through this upper inner arm of the circuit. And so in this case, well, now we've got 2 resistors here, a pair of resistors here, R2 and R2, that are in parallel with one another. And so I drew that circuit. So in this case, the current must flow through R1. That's the first resistor in this outer arm. Then it can flow through either of the 2 R2 resistors, the upper path or the lower path. And then the current, all of the current must again flow through R3. So this is a bit more complicated arrangement. Here we've got 2 resistors in parallel, R2 and R2, and then that arrangement is in series with 2 other resistors, R1 and R3. The third circuit, this is now when the switch is positioned such that it's in position B. In this case, this lower path on the inside of the circuit diagram, now this is activated. And what this path does is basically shorts out the resistor R3, i.e. there's a resistanceless path, just a wire, for all of the current to flow around, avoiding R3. So in this case, with the switch at B, current flowing out of the battery will pass through R1, then R2 at the top, and then just via a wire back to the battery. And so this is the case with switch in position B, that the circuit is again just a series circuit, but now it's just a series circuit involving resistance R1 and R2. And so that's this picture here. So my next step is to take those 3 pictures and write down Ohm's law, the relationship between the voltage, the current, and the resistance for those 3 pictures. And when I'm writing down Ohm's law, I'm going to also use kind of the rules for how you combine resistors in series and parallel. If there's resistors in series, you just add their resistance to get the equivalent resistance. If resistors are in parallel, then you add the reciprocals of the resistances to get the reciprocal of the equivalent resistance. Let me just make a comment downstairs here that when I write down Ohm's law, I'm going to write down it in this fashion, that the ratio of the voltage to the current is equal to the resistance. That's a version of Ohm's law. I'm going to write it down that way because I know the voltage is 6 volts, and I know the currents in the 3 situations. They're 1, 1.2, and 2.0 amps. And we're going to be interested in finding the resistances of the resistors. So that's the reason I've written it this way around. Let me also comment on the units. This is how I'm going to write the units. Volts for the potential that's provided by the battery, and amps for the current that's supplied, and then that's going to give me ohms when I take that ratio for the resistance of the resistor. And when I write down the equations, just to keep things simple, I'm not going to keep writing these units in here. I'm just going to write expressions for the resistances of the circuits, which are in ohms, in terms of the ratios of the voltage to the current from the battery and flowing through the battery. So let's go ahead and write down these three equations. So in the first circuit, where the switch was open, we've got 6 volts divided by 1.0 amps. And I'm being naughty, right? I'm not writing down the units because I'm trying to keep things simple. That is simply 6. It's 6 ohms. And that's equal to the total resistance of this arrangement of 3 resistors in series, which is just the sum of their resistances. So that's an equation from this first circuit that relates the values of the 3 resistances. We know if we add them all up, we're going to get 6 ohms. Let's do the same thing for the second circuit, where the switch is in position A. So in this case, we've got 6 volts divided by 1.2 amps. Again, I'm being naughty. I'm not putting in the units, just to keep things simple in this case. That ratio is 5, and that's equal to the resistance of this circuit here. Now, 2 equal resistors in parallel with one another have a resistance that's half their individual resistance. That's a special case of the equivalent resistance being the sum, the reciprocal of the equivalent resistance being the sum of the reciprocals of the individual resistances. If you've got 2 equal resistances, then the equivalent resistance is half of their individual values. And so this resistance here of R2 and R2 in parallel with one another is R2 over 2, and then that's in series with R1 and R3. So the resistance here is R1 plus R2 over 2 plus R3. And so that's a second equation that relates the 3 resistances and says that if you add up R1, R3, and half of R2, they add up to 5. Finally, the last circuit here. In this case, the battery supplies 6 volts. The current flowing in the circuit is 2.0 amps. That ratio is 3. Again, I'm being naughty, not writing down the units. And that's equal to, that's 3 ohms, and that's going to be equal to the sum of the resistances of this arrangement, which is just 2 resistors in series with one another. And so it's just R1 plus R2. That's a third equation. A third equation that simply says that the sum of R1 and R2 is equal to 3. So here we've got 3 equations containing 3 unknowns. 3 equations for the 3 circuits, open, A, and B for the positions of the switches, with 3 unknowns. They're the R1, the R2, and the R3. And so 3 equations with 3 unknowns, you can solve it, just like 2 equations, 2 unknowns. So let's go ahead and do that little bit of math. Okay, the way I solve this problem is by first taking the following combination. I'm going to take equation number 1, and I'm going to subtract off equation number 3. And when I say I'm taking equation number 1 minus equation number 3, I mean on the left-hand sides of both equations, I'm going to subtract 3 from 1. On the right-hand side, for both equations, I'm going to subtract 3 from 1. So if I subtract on the left-hand side equation 3 from 1, that would be 3 minus 6. So that would be 3. And then on the right-hand side, if I subtract equation 3 from 1, well, the R1 and R2 in equation 3 will cancel with the R1 and R2 in equation 1. I'll be just left with R3. And we've immediately found that the resistor R3 is 3 ohms. The next thing that I did was actually to subtract from equation number 1 again, equation number 2. Again, that means I'm subtracting the left-hand side of equation 2 from the left-hand side of equation 1 and the right-hand side of equation 2 from the right-hand side of equation number 1. So let's do the left-hand sides. We're going to have 6 minus 5, so that's going to be 1. And on the right-hand side, we've got R1, R2, R3 minus R1, R3, and half of R2. So we're going to be left with an R2 over 2 when we do the subtraction. The R1s and the R3s cancel out. Well, if you look at this equation, it tells us then that R2 must be 2 ohms. So that's the solution for that second resistor. Now we've got 2 of the resistances of the resistors. We only need to find the third one, R1. For this, you could actually use any one of the 3 equations on its own. I'll just use equation number 3 as its simplest. And we're just going to plug in the values of the other resistors that we know. So if we look at equation number 1, it says that 3 ohms equals the sum of R1 and R2. R1 we don't know, but R2 we do know. It's 2 ohms. And so R1 must be 3 minus 2, must be 1. And so in that way, we found the resistances of the 3 resistors. So just to summarize, in that case, we had a pretty scary looking circuit with actually a multi-way switch in the circuit. By flipping the switch to different positions, we could reconfigure the circuit. That circuit was, in general, an arrangement of series and parallel resistors. We were able to draw the circuits, firstly, with the switch in the different positions, write down Ohm's law describing the circuit in the 3 different switch positions, and then solve those Ohm's law equations for the individual values of the 3 resistors. We had to use Ohm's law, we had to use our understanding of series resistors, our understanding of parallel resistors, and our ability to analyze an electrical circuit.